All right. I will begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for this opportunity we have just to meet and to study your creation. I thank you for these students. Just ask you to just bless this class, bless this semester. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me start at the beginning. So today we're talking about matrices and in particular matrix algebra. Really matrices and proofs is kind of the big idea today. Proof via index notation, which is almost certainly something you didn't do in 221, right? But before even that, I really need to set the stage here, all right? So I want to talk a little bit about abstract algebra, right? So we have different concepts, like we have a ring. So what is a ring? A ring is a set which has an addition and a multiplication, all right? And the addition and multiplication behave in the usual way, all right? Although it could be non-commutative, so that's not quite the usual thing, right? But if we talk about a commutative ring, with identity, I'm going to denote that by R. So a commutative ring with identity is essentially a set of numbers where you can add, you can multiply. The multiplication satisfies the, like, A times B is B times A. And you also have like the distributive property. A plus B times C is AC plus BC, and so forth, right? The multiplication's associative, the addition's associative, there's such a thing as zero. And if I say identity, that means there's a number 1, something that behaves as the multiplicative identity in the ring, all right? So examples of rings, there are many examples of rings. So this could be, for instance, it could be the rational numbers. Actually, it could be the integers. It could be the real numbers. It could be the complex numbers. These are all examples of commutative rings with identity, right? There are more exotic examples we could give. I wonder how many of you guys know what this is, Z sub n? Do you guys know about this one? Like modular integers? Show of hands, who has seen modular integers already? So who has not seen modular integers yet? So a few of you. Okay, so I won't be too technical. We're just going to be kind of a little bit formal in here. But essentially, this is the set of numbers 0, 1 through n minus 1, all right, where multiples of n are identified with 0. All right, so I have a 30-page appendix in the notes that builds this concept up from the base by establishing an equivalence relation on the integers, where we say two integers are equivalent if they differ by a multiple of n. That defines an equivalence relation. It partitions the integers into multiples, all right? And then those equivalence classes themselves can be added or multiplied in a natural way. We don't need to do all that in here. This is not an abstract algebra course. I just want it as an example, all right? So if you'll forgive me not building this from the ground up, let me just give you some examples of how it works, all right? So like, here's Z2. It's got 0 and 1 in it, all right? Now these zeros, this 0 and 1 is not the 0 and 1 you're used to. If I want to be like annoying and just make it feel a little bit different, I'll slap a bar on it, okay? There, now you see it's different, there's bars on them. And so like here's the rules. 0 bar plus 0 bar is 0 bar. I'm already tired of writing the bar. 1 bar plus 1 bar is 2 bar. You just add the numbers under the bar. But the new thing is, in Z mod 2, 2 is 0. So that is 0. All right, 0 bar. Or if you want to drop the bar notation, we have the equation 1 plus 1 equals to 0. All right, so 1 plus 1 is equal to 2. Well, not always. All right, not in Z mod 2, because 2 is 0, which is a troublesome thing. Okay, so Z3. Is it okay if I don't write the bars? Because it gets really old really fast. Understand, though, that the modular integers, the addition and the multiplication is a non-standard addition and multiplication. Technically speaking, we've defined an operation on sets of integers, and it's logical. It's shown in the appendix. And I would, well, anyway, if this is a number theory class or abstract algebra, maybe I get into it more. But let's just, I just want it for an example. I've already spent too much time. 0, 1, 3. So like here in Z mod 3, 1 plus 2 is 3, which is 0. Context matters here, right? 1 plus 2 is not 0 in Z mod 2, it's 1. What else? How about 2 times 1? 2 times 1 is 2. Well, that's kind of boring. 1 is the multiplicative identity. All right, what's 2 times 2? It's 1, yeah, it's 4, right? But like you said, that's 1 in Z mod 3. And so what this means is that the multiplicative inverse of 2 is equal to 2 in Z3. That's kind of weird, right? Now we don't write 1/2 in this context. That is a forbidden notation. If you write that in Dr. Sprano's class, he will be very annoyed. I'm pretty sure. Anyway, well, I'll shut up. All right, so how about Z6? Let's just do that. Since many of you don't have any experience with this already, let's talk about this. This is just, it's a good use of our time. I think it's helpful for you guys to have seen this before abstract algebra, to get it in your system, to let it kind of percolate, so that by the time you get to abstract algebra, you already have some intuition about these things. You're not seeing it for the first time, as an example, in abstract. And it's also an interesting playground for linear algebra. Some of the results, we can study results over this, just like we can study results over the rationals or the reals or the complex numbers. So Z6 is interesting, because in Z6, okay, so let's check it out. 2 times 3 is what? Well, not 2 times 3. I want to do 2 times, 5 times 5 is what? Yeah, it's 25, which yeah, it's straight to the point, it's 1. So, aha, well, 5 inverse is equal to 5, apparently, in this case. That's kind of funny. This does not always happen, all right? For instance, in Z11, 3 times 4 is 12, which is 1, right? So 3 inverse is equal to 4 in this universe over here. But Z6 is different. Z6 is fundamentally different than Z11 or Z3 or Z2, all right? Z11, Z2, and Z3, these are all examples of fields. What's a field? A field is a commutative ring with identity such that every non-zero number has multiplicative, I can't spell, identity. In other words, a field is a set in which every non-zero element is a unit. A unit in abstract algebra is an element with a multiplicative inverse. So in Z2, the only non-zero number is 1. 1 is its own inverse. In Z3, 1 is its own inverse and 2 is its own inverse. Everything's got an inverse except for 0, fine. In Z11, well, I haven't done it all, but you can check. All of the numbers here except for 0 have a multiplicative inverse, right? Like 3 and 4 are inverses of each other. Z6 is not a field, though. You see, because check this out. 2 times 3 is what? Is 6, which is 0. All right? Suppose 2 inverse exists. And then what? Well, then we can do 2 inverse times 2 times 3, which would be 1 times 3, using associativity and multiplication. Sorry. Which would be, well, that would be 3, right? Yet, it's also equal to 2 inverse times what? Times 0, right? Because I'm multiplying this equation here by 2 inverse on both sides. On the one hand, I got 3. On the other hand, I got 0. But if you study the development of these objects, Z6, 0 is not equal to 3. 0 is essentially, it's a set of integers that are, one way of looking at it, it's a set of integers which are multiples of 6. Whereas 3 is multiples of 6 plus 3, that whole set of things. I mean, that's one model of these things. All right, anyway. Philosophy aside, 2 and 3 don't have multiplicative inverses here. Therefore, Z6 is not a field. But it's still a commutative ring with identity. This phenomena is an important phenomena. These are called zero divisors. Zero divisors are trouble, right? This semester, we're going to study linear algebra, which is the study of vector spaces and linear transformations. Our scalars are going to be taken from a field for the most part. That's important. The non-existence of zero divisors is part and parcel of what makes linear algebra not a nightmare to understand. If you try to take linear algebra and instead do linear algebra over just a commutative ring with identity, that's a much harder project, right? Many of the theorems still hold, but it's much more nuanced. Anyway, so I have now totally off track for my lecture. But anyway. Okay, so we'll get this over with here. So another sample calculation in example 1. Suppose you've got in, let's say, Z5, you got the matrix A is equal to, I don't know, 1, 2, 3, 4. How about that? All right. This would be, so technically speaking, in my notation, man, this is all out of order. I'm sorry, guys. This is, in my notation, this would be Z5 2 by 2. It's an element of the 2 by 2 matrices with entries from Z5. Does this have a multiplicative inverse? Well, the cool thing is that 2 by 2 inverse formula you learned in 221, it's still legitimate in this context. Like the calculation which supports that works over a commutative ring with identity, provided that the division in that formula makes sense. So the formula then is this: A inverse is, well, let me write it this way. Fine. So we got to do 4 times 1 minus 2 times 3, inverse of that. And then what do? We flip the diagonals, and we put minuses on the off diagonals, if I remember right. Is that right? Like, if you got A, B, C, D, you invert it. The formula is AD minus BC inverse. Flip the diagonals, put minuses on the off diagonals. That's the formula for the 2 by 2 inverse, right? This formula still makes sense in this context, actually, but we have to be careful to understand the inversion of the number in light of this new funky arithmetic. Yeah. All right, so it's not that hard, though. We got what? 4 minus 6 is minus 2. Minus 2 inverse. Fine, I've got 4. Here's some fun games. 2 is 3. 3 is 2. Minus 3 is 2. 1 is 1. What's 2 inverse? Well, it's the same as 3 inverse, right? Because 3 is equal to minus 2. So the rule is in Z5, you can add multiples of 5. That's the basic arithmetic here. That's the idea. Anyway, so notice that 2 times 3 is equal to 6, is equal to 1 in Z5, which means that 3 inverse is actually what? 2. So this is 2, 4, 3, 2, 1, which is going to give me 8, 6, 4, 2, which I can simplify, drop off copies of 5, you know. So 8 minus 5 is 3, 6 minus 5 is 1, 4 is 4, 2 is 2. So allegedly, that is the inverse of that matrix. Now how can we check if we're right or wrong? Yeah, multiply it. Right, so good. And you guys know how to do that because you have taken Math 221. So this should not be a heavy lift, except what's the newfangled thing here? I'm working over Z5, right? I think it's fun. Give you guys something a little bit new. So this gives us 3 plus 8, please work. 3 plus 3, 9, plus 16, 1 plus 4, 3 plus 8, which in deedly doodly is 11, which is 1, 5, which is 0, 25, which is 0, 11, which is 1. Hooray! So it works. When I actually write your homework, I'll probably give you guys one of these, all right? And then you can do it and feel good about. I just think this is a nice way to learn a little bit of modular arithmetic without, you know, it's kind of low, not very stressful. All of a sudden, if you start thinking about systems of equations, though, this is interesting because if you think about how what you did in 221 is going to change, it's going to be really different, right? Anytime you've got a parameter in the solution set, if it's a Z5 problem, that parameter can't take infinitely many values. It can take 5 values, right? So like the counting of solution sets becomes much more interesting. I mean, in working over the reals or the complexes or the rational numbers, what's the story? The solution set either has what? Nothing at all, it's inconsistent, right? It's got just one thing because it's a consistent system, right? What's the other possibility? It has infinitely many solutions. That's it. Them's your choices, right? Now the dimension of the all right. One lecture at a time. All right, so I did have other things to cover today. Now we never have enough time. All right, I'm going to stop. Okay, so you guys know what a commutative ring with identity is a little bit. It could be any of your favorite reals, rationals, complexes, and it could be something new, like these modular integers. All right. I think that's pretty much it for here, at least for a long time. That's all. That's the extent of our examples. Okay. Oh, there is one other thing. A set of polynomials would be like this. Polynomials you can multiply to get a polynomial. You can add them. 2 polynomials you get a polynomial. The constant number 1 serves as a multiplicative identity. So like the set of polynomials is a commutative ring with identity. That's a kind of interesting example you guys could understand without, you know, reinventing the wheel or something. So anyway, you're like, well, why are you talking about a commutative ring with identity? Because you're going to focus on fields this semester, right? Yeah. Mm-hmm.
And associativity always follows commutative?
No, these are, you know, that's a good. Does associativity always follow commutativity? I wouldn't even. I don't think about. Honestly, I always think about something being associative and then adding commutativity to it. So it's hard for me to answer your question. For me, that's how I think. Now, that would be a good question, like ask Dr. Sprano. You know, because he thinks more about these things at the moment. Or I could think about it after class, but in my current frame of reference, that's a very hard question. Can I think about commutativity outside of associativity or vice versa? I always start with associativity of the object and then add commuting as a, you know. So commutativity is AB is equal to BA for all A and B. Associativity would be A times B times C makes sense. So associativity has to do with 3 things. It's like A times B times C versus A times B times C. Okay, enough. So our m by n is the this is matrices, m by n rows, columns, with elements or entries, if you like, from R, right? Now, by convention, Rn is, oops, not trying to keep it real just yet, R n by 1. So this is the set of column vectors. So to complete the thought, I stopped mid-thought, is the reason I'm showing you guys this over a commutative ring is we don't actually need division until a little bit later in the story. So like all of the basic addition and multiplication, we can do over a commutative ring in as much as we don't care about division. So why not do it in that generality since it's the same trouble, all right? So if I have a matrix, let's say A, and I have A and B in both m by n matrices, can I add them? Well, first of all, some ideas. A is equal to B if and only if Aij is equal to Bij, right? For all I and j. And by for all I and j here, of course, I mean I ranging from 1 to m and j ranging from 1 to n, right? So that's equality. Like equality of two matrices is judged by whether or not they're matching in every single component, right? This is the equality. How would we define A plus B? What's the definition of A plus B? Well, A plus B, to define it, I can just tell you what the ijth component of it is. And what is it? It's equal to Aij plus Bij, right? So that is the definition of matrix addition. Just that. And likewise, if I've got a constant times A, the scalar multiple of A, that's just C times Aij. So this is the definition of matrix addition and scalar multiplication. All right. How do we define matrix multiplication? How will we do that? Any ideas? Dot product first. Ooh, yes. Not here, though. So here, we're just going to use index. We're going to use the index formula to define it. Now, that dot product thing you're talking about, it's well and good. That's a good way to calculate. But, like, here's the way. So if we have A in, let's say, our m by p and b in our p by n, then AB, the ijth element of it, is equal to the sum k equals 1 to p of A I k b k j. Right. And that's, of course, for 1 less than or equal to I, less than or equal to m, 1 less than or equal to j, less than or equal to n. We need for the number of what? The number of columns in the left multiple, the left factor to match the number of rows in the right factor in the product AB. Right? We have to have that matching between rows and columns of the matrices which are multiplied. Otherwise, we can't form the matrix multiplication, right? There doesn't seem to be a well agreed upon name for matrices which you can multiply. I sometimes call them multipliable. There are books which call it conformable. But of course, you have to have, the dimensions matching, otherwise you can't do this, right? And this is also to be understood in the context that like A or B is either a row vector or a column vector. You drop one of these indices. So like one of the indices just goes away, and you have to interpret this formula in the correct way for row and column vector. We'll come to that when we come to it. So there's your definition of matrix multiplication. How about transposition? How do we transpose a matrix?
Without using formal notation, I guess change the columns to rows.
Yes. But this will not work for a proof. So what's our definition? I mean, you're not wrong, but yeah.
A transpose IJ, A, J.
There you go. So there is a definition. So we want to give definitions in terms of index notation. So we have concrete, specific definitions. We can prove things. So you're like, what do you mean you can prove things? Well, let's see if we can prove some things. Yeah. Let's take these definitions for a spin and see what we can do. So this will probably be another one of your homework problems, is to do a proof like I'm about to do, but for a different one, you know. So here's a claim. A times B plus C is equal to AB plus AC, right? And I'm going to assume that the matrices are multipliable. By the way, you can only add two matrices if what? They have to be what? The same size, right? Yeah. So like the full definition, there's more here. If you look at my notes, the full gory definition is in the notes, right? I can only write so much on the board. This is why I type careful notes, so you have the full thing over here. I try to communicate more the spirit of the thing in class. But yeah.
With the definition of matrix multiplication, is that supposed to be B sub nj? Because n is a constant and doesn't...
That's a K.
Oh, that's a K. Okay,
Yeah.
I just misread that.
That
makes a lot more sense.
Yeah, those are K's. My bad. It's okay. I'm sorry, that's horrible. It's truly horrible. Okay, so here we go. So A times B plus C. We're going to calculate the ijth component of this guy. All right? So by definition, this is the sum. K, let's say, equals 1 to P. I'm assuming that like A is A and R M by P, whereas B and C are in R P by N, let's say. So we got A, I, K, and then parentheses B plus C, K, J. Now this, over here I write the reason. This is the definition of matrix multiplication. Definition of matrix multiplication. That's what I used for that step, right? What's my next step? My next step is to use the definition of matrix addition. See, next up, we've got the sum K equals 1 to P, AIK, BKJ plus CKJ, right? So here's definition of matrix addition. Yay. What next? Notice here that AIK, BKJ, CKJ, these are all just numbers, right? So by assumption of the properties of a commutative ring with identity, we have the distributive property. So for each choice of index here, we can do the following. We can go, oh, okay, well that's the sum K equals 1 to P of like AIK, BKJ plus AIK, BC, my bad, C, KJ, all right? And that's just by properties of commutative ring, right? Just assume the distributive property of commutative ring. Now what? Well, now we use a property of finite sums. The sum of a finite sum of a sum is the sum of the finite sums. So you all know it, right? You proved it. I'm sure you proved it somewhere. It's a lie. I know you didn't prove it anywhere, but you'll believe me that it's true. So that makes it right. Right, so this could be proved, that the sum of a sum is the sum of the sums. We could prove that inductively. So anyway, this is property of finite sums. And then I just apply the definition of matrix multiplication again. See? What am I looking at? This, my friends, is AB what? Plus AC what? See, this is summed over. We've got a free I and J index. So that's ABIJ. And this here is ACIJ. And then what? So definition of matrix multiplication. I sure hope this is the one I did in the notes. Otherwise, I'm almost certainly going to give you a homework, which I have published a solution for, which would be so embarrassing. Let's see here. I'm just kidding. I think I'm kidding. Where was I? Oh, yeah. So then what? So then we use the definition of matrix addition again, right? So this is AB plus AC IJ, which is, again, the definition of matrix addition. And this is a fairly typical proof of the matrix properties. Like almost every matrix property can be proved with a calculation similar to this. Now the proof's not quite complete. There's a concluding sentence. What's the concluding sentence? Thus, A times B plus C is equal to AB plus AC, since the above holds for all I and J, right? And two matrices are equal if they have the same components everywhere, right? So that's the deal. So like you could prove the associativity of matrix multiplication through a similar but possibly more tedious calculation. And what you'd find is that at the base of everything, the associativity of matrix multiplication ultimately rests on the associativity of the numbers which are being multiplied inside the matrices. So like the distributive property of the matrix multiplication, where's it coming from? In some sense, it's really coming from the distributive property of R itself, right? And the fact that matrix multiplication and addition play well with that distributivity. Okay, so another thing I should give you a definition for definition. Well, let me start with the first thing. Delta ij is 0 if I is not equal to j. It's 1 if I is equal to j. This is the so-called Kronecker delta. This is a very useful notational device. And we can define E sub I, an element of Rn, by E sub I, the jth component of it, is equal to Kronecker delta ij. This is the so-called standard basis. So like, for example, in R3, you've got E1 is, 1, 0, 0. E2 is 0, 1, 0. This should kind of be like familiar, right? I hope you did this in 221. You guys did use this notation in 221, right? Yeah. Now, so just so you know, we use this sneaky notation like so. So because I don't always want to write a column vector, if I write parentheses, it's my implicit column vector notation. If I want to write a row vector, I'll use square brackets on the row. All right? Now there's another thing I should define, which is Eij. So this is an element of our m by n. And here's how this goes. Eij, the kth component of it, is equal to Kronecker delta ik Kronecker delta jl. And here's where we run up a little bit of trouble in terms of terminology, but this is called the matrix units. they're all 0 except the ijth entry, which is 1. And I say, yeah, but the word units here is unfortunate in regard to like the use of unit I used earlier today, right? These do not have multiplicative inverses. Like, certainly not. All right, they do not even close. Now, we can use the standard basis, which is E1 through En, to build any column vector. We can use the matrix units to build any matrix, right? So like, here's the long and short of it, is if I've got, m by n matrix A, I can write it as the sum. Let's say I equals 1 to m, sum j equals 1 to n of A, I, j, E, I, j. So any matrix can be written as a sum of matrix units. Now this is an example of something which I wanted to talk a little bit about today. This is an example of a finite linear combination, right? So, like, what's a linear combination? I mean, you guys saw it in 221, right? For vectors. If we take vectors and we multiply by numbers and we add them together, that's a linear combination. Same thing in here. We can talk about linear combinations over a commutative ring. If we've got some way of multiplying the objects by numbers in the ring, then we can take linear combinations of them. Now you can prove that this formula is legitimate by supposing, like, if you just, if I say b for a second here is equal to this, right? And I calculate bij, what do I get? Well, instead I and j is kind of loaded here. Let's say bkl. So that would be, I would take the klth component of all this, right? So let me, for the sake of not writing too much. So suppose we have b is equal to this, right? And I calculate the klth component of that, right? How would that go? So by definition of matrix addition, I can basically do this, all right? By definition of matrix addition, I can do that. And then by definition of scalar multiplication, I can do this. Then by definition of the matrix units, what's this? Delta IK, delta JL, right? And what does that do? This makes the sum 0 except for what? So like IK is only non-zero when I is equal to K, which just leaves us what? A, so we have the sum. I'll leave the sum over. Let me just get straight to the point here. We get a KL if you think through it, because the sum over J collapses because the only thing you get is L equals to J. Everything else is 0 because this is only non-zero when J is equal to L. So the sum over J just picks out the L one. And the sum over I collapses to just the term I equals to K for the same reason. So both of these sums vanish until just the one thing is left, this, right? But what this shows is that if B is equal to the thing in red, the KLth component of B is equal to what? AKL, right? So these two matrices have the same components. Therefore, what I wrote to start with is true. A is equal to the sum over I and J. If you'll allow me that briefer notation, I'll allow you to. IJ. So any matrix can be written as a sum of the matrix units, like that. So let me show you some stuff in the notes here before I forget. So, like, I really just need you guys to read sections 1.1 through 1.4. I don't think you're going to find anything in here as like super complicated or new. I did want to do an induction proof. I think I'm out of time for that today. Let's see here. So yeah. So it would be good for, I would like for you to read the notes here, just to remind yourself like the properties we know for matrix multiplication and stuff. Some of these things might be new to you if you haven't had my course, like A times B can be understood as, the column by column multiplication of A on B. This is the column by column multiplication rule. This is sometimes very useful. There's also a row by row rule. The things you're less likely to have seen if you didn't have my section of 221 is probably the things which come next. There's like 5 different ways to look at matrix multiplication, right? But certainly the one I showed you as the definition here is by far the most convenient for proofs. Because you don't want to be writing out ... full matrices to prove something. That's a horrible notation to prove things about matrices. I've seen students try it on test. It never goes well. These formulas are near and dear to my heart. We can use the standard basis times matrices to do things like pick off multiplication by EI picks off the ith column, right? Multiplication by the so transpose gives us a row vector, like you said. Row vector times A picks off the ith row of A. So this is ways of producing rows and columns by multiplication by the standard basis or its transpose. If you you can literally build the matrix units from properties, outer products of the standard basis like this. So you can construct the matrix units with the standard basis by this simple formula. Super useful if I ask you homework problems about properties of the matrix units, because you can use this and the fundamental identity, which is in example 3.20, that basically the dot product, like you're pointing out, Sam, dot product, right, of EI and EJ is exactly that. It's the Kronecker deltas, because the standard basis is in fact what we call an orthonormal basis. Although that is a very foreshadowing comment. We won't get back to orthonormality until the third part of the story in this course. Now, what is EIJ times a matrix? It's kind of weird. I don't have any intuition about that, but there's what it is. It puts the ith column in the jth column spot and makes everything else 0 apparently. And that's weird, isn't it? Here's an example of that. Anyway, in summary, these are all of my favorite formulas about how the standard matrix and the matrix units work. Like any vector can be built as a sum of them. In this way. We can pick off columns and rows, and we can build the matrix unit from the standard basis, all these things. This is also very useful. To select the ijth component, we can multiply sandwich between the transpose and the other thing. Now, so just to wrap things up here today, the next section I define the identity matrix. I define what we mean by, invertible matrix. You guys remember, if you have a product of two matrices, it's the identity matrix, it's invertible. Same thing goes here. There's the thing we did in detail earlier. Here's a rotation matrix, exciting. Here's the properties of the matrix inverse. These things are still true over a commutative ring with identity. The proofs are right below. I'll probably go through I'll probably go through this example. I'll probably go through that argument next time because I want to do an induction in class. This right here I won't do in class, but proving the laws of exponents for matrix multiplication is actually somewhat technical. Here's the argument that a to the p times a to the q is equal to a to the p plus q, and also the a to the p to the q is a to the pq, and that, like, it's involved actually proving those. It actually takes some work, but it's all induction. But we'll assume that those things are true, because that's really more abstract algebra. It is, however, not the true for products, because a times b is not b times a, so like ab to the p it's ABA, it's ab, it's not a squared b squared, because matrices don't commute. Finally, I would hope that you know what a symmetric matrix is, an anti-symmetric matrix, some basic properties of transpose. What's a triangular matrix? It's a matrix that's either 0 above or below the diagonal, right? What's a diagonal matrix? Just non-zero on the diagonals, right? We know that. And then last but not least, and oh, by the way, here's some here's how to do those things in like index notation. So I'll probably ask you guys some simple homework problems based on this reading, just to, you know, try to make sure it sets in. And then finally, these are good examples of like matrix-based, index-based proofs. And then finally, you can have a nilpotent matrix is a matrix that some power of it is 0, yet its power less than that is not 0. That's a nilpotent matrix. Those are important. And then finally, block matrices. What's a block matrix? You guys know?
Matrix of matrices.
Whoa. It's a matrix of matrices. That's a very good answer, yeah. So essentially, the point is that if you have block matrices, you can multiply them as if the blocks are themselves numbers. But you have to be careful to keep the numbers in order, because matrices don't commute. This is block multiplication. And so I'd like you to know about that. We'll come back to all of these things in due course, but I just wanted to throw it out there. If you've never seen these before, read my chapter more carefully, please. Anyway, that's it for today. Thanks, guys. So next time I'm hopefully mostly doing like solution sets and systems of equations, a quick review of that basically, okay?